In this section, we're going to talk about statistical modeling. So in a statistical model, we are trying to come up with, let's say, a simplified version of the world. We do this by making some assumptions around the relationship between the input and the output variables. So the first kind of assumption we're doing is around the type of relationship between the input and the output variables. The most common assumption is that the output variable can be predicted through an additive relationship of the input variables. For example, y equals x1 plus x2. However, there are other types of assumptions that we can make. For example, we can assume that there is a multiplicative relationship between the input and the output. The second thing we do is make an assumption around the distribution that our data or our error follows. So in linear regression, for example, we assume that the error is normally distributed. In Poisson regression, we assume that our response variable is distributed according to a Poisson distribution. But finally, there are also some models where we don't make any such assumptions. There are many different statistical models. It could take decades to study all of them. We're going to deal with some of the most common ones, and we'll also provide resources in the additional content section for these ones. The most common statistical model has to be linear regression, followed by logistic regression, which extends the logic of linear regression to data that is not normally distributed. And then we have some more advanced models, such as the generalized additive models, Bayesian models, and splines. Let's start with linear regression. So in linear regression, we assume that there's a linear relationship between the inputs and the outputs. So that is, we can predict the output by simply adding up the input variables times a coefficient. We assume that the error is normally distributed. There's no collinearity between the input variables, and we also assume the homoscedasticity of the errors. We'll explain each one of these in turn. So here's the definition of a linear regression model. We have a response variable y, and we assume that we can predict this through a relationship of this form. x1, x2, xn are our predictor variables, and c1, c2, cn are the coefficients of those variables. Epsilon is an error term which we assume is normally distributed with mean 0 and variance which we have to infer from the data. So for example, in practice, this is what the linear regression equation would look like. Sales equals minus 1.2 price plus 2.3 quality. So this graph here shows very well how linear regression works and the assumptions behind linear regression. So we have values for the x variable and we want to predict variable y, and we assume that we can model this using a straight line, and at each point where we make a prediction we assume that there is an error which is normally distributed. So essentially the prediction at each point follows a normal distribution where the mean is given by the linear regression equation and the variance is inferred for the data. We mentioned that one of the assumptions is the homoscedasticity of errors. This means that everywhere across this line, the variance sigma remains the same. So the only thing that changes as we move across this line of prediction are the values of the input variables. The variance and the coefficients, they remain the same. But why should we assume that our error is normally distributed? Well, first of all, we know that there is no chance we can find a straight line that perfectly connects the input and the output data. It just doesn't really happen in nature. So there's always going to be some error. So actually we can fit a straight line using the least squares estimator without having to assume that the error is normally distributed. However, making this assumption provides a good theoretical justification behind the least squares estimator. This estimator is unbiased, a very important property in statistics, which might not mean much if you're just a practitioner. However, the important bit is that this assumption, the assumption of the normally distributed errors, lets us calculate p-values for the coefficients of each variable. So like with all hypothesis tests, a low p-value means that the coefficient is significant, and hence this variable is connected to the output variable. And the coefficient is also telling us the direction of this effect. So in this example, we used R to fit a model on a dataset called empty cars. So empty cars is a dataset provided by native R for learning and experimentation. Before I go and explain about the coefficients, I need to explain the goal of the dataset, which is to predict the miles per gallon consumed for different types of cars based on various variables. So in this model, we used only 3 variables just to make things simple: the number of cylinders, the horsepower, and the number of gears. So R has estimated the different coefficients for us, and then these estimates they translate in this equation here, that miles per gallon equals 25 point blah blah minus 1.2 cylinders, etc. Something which we didn't mention earlier is that in linear regression we always add an intercept term, which is a constant that improves the performance of the linear regression model. However, it doesn't really have much of an interpretation, so we don't care so much about it. What we care about are the estimates of the coefficients for the different input variables, as well as the p-values for those tests. So for each coefficient, we perform a significance test where the null hypothesis for the coefficient test is that the real value of the coefficient is 0. That's essentially like saying that this variable is useless for predicting the target variable. And as you can see, R here helps us by giving 1 star to the horsepower variable, which 1 star means that this variable is significant at the 5% level. In linear regression, besides the significance, we also get the direction of the effect. So we can see that in this case it's negative, and adding 1 point to horsepower reduces the miles per gallon by this amount. In linear regression, we also perform another test for the overall model. So in R, you can see the results down here, and you can see a very small value for the p-value. So that's 4.19 times 10 raised to the power of minus 9. So that's practically 0. So the null hypothesis for the overall regression test is that the model we have created is not better than an intercept-only model that simply predicts the mean of the target variable. So what this means is that if the p-value is very small here and we reject the null hypothesis, then our model is essentially significant and useful. In the R output, you can also see the adjusted R squared and the multiple R squared, where when we talked about metrics, we mentioned that these are metrics that we use to estimate the performance of regression models. So the adjusted R squared gets a value between 0 and 1 and penalizes models that contain more variables. So this number here means that the model performs quite well overall, as the value is quite close to 1. We also mentioned about collinearity. We said that one of the core assumptions of linear regression is that the variables are not collinear. So what happens when the variables are very highly correlated with each other? Well, the thing is that linear regression estimates the effect of each variable independently of each other. So if the variables are dependent, then this becomes impossible. We get very unstable coefficients, which means that by adding or removing a data point, we might get very different values for the coefficients. Secondly, we have very low statistical power. So the p-values might be very high and the tests for the coefficients might not be significant. However, in reality, they should be. So the way to solve this is to basically remove some of the highly correlated variables. And in order to detect which variables are highly correlated, we run either a correlation plot, or we can also run a test called the variance inflation factor, and we talk more about this test in the additional content section. So we mentioned that the most important assumption behind linear regression is that the error is normally distributed. So how do you test for this assumption? You test for this assumption by checking the distribution of the residuals. So the residual for an observation I is simply the difference between the real and the predicted value. So through the residuals, we can test for the normality assumption, for the dependence assumption, for the homoscedasticity assumption, and we can do this through graphical means. So there are some key assumptions with regards to the residuals that we need to test for when we perform a regression analysis. These are the 3 assumptions around the residuals. First of all, the error must be normally distributed. Secondly, the error needs to have constant variance. And finally, the residuals need to be independent of each other. So a way to test for these assumptions is through graphical means. So testing for linearity can take place through graphical means in the following way. So on the left-hand side, you see two plots where the assumptions are not met, and on the right-hand side, you see two plots where the assumptions are met. So over here, you see a relationship between x and y that involves some curvature. So it could be better modeled perhaps through a square relationship instead of a simple linear relationship. And you see that when we plot the residuals of this model, we get this. So it's clear that the residuals are not randomly distributed across the space. Instead, what we wish to see is something like that. So when the relationship between x and y is linear, then the residuals are randomly and uniformly scattered around the space. We also need to test for homoscedasticity. So homoscedasticity is the assumption of constant variance. So let's say we have identified that the residuals are indeed distributed in a uniform and linear way. However, that's not enough. We need to make sure that the variance is constant, because if the variance is not constant, then the residuals are not normally distributed. So here again are two examples. On the left-hand side, you see a case where the variance of the residuals is not constant. So we call this phenomenon heteroscedasticity. And you can see that here we are modeling x against y. And you can see that as x increases, so does the variance increase. There are some cases where this can happen, some specific problems. So when we plot the residuals, this is what we see. We see that the errors get larger and larger as x increases. So that's not what we're after. Once again, what we want to see is something like this plot. The variance is constant and the residuals are uniformly distributed across space. So in this case, when we are facing heteroscedasticity, there are some other models that we're going to cover later, which can actually deal with this issue. And finally, we expect our residuals to be independent. Once again, this is the residual graph that we hope to see. So when the residuals are not independent, we're going to see some patterns, such as a linear pattern or a sinusoidal pattern or some other curvature. This means that, for example, one data point influences another data point. This happens quite often in time series, for example. So if you're trying to predict things in time, let's say the sales of a product, it's very likely that the sales today are related to the sales tomorrow, and they will not be very related to the sales 2 years ago, let's say. So we might also expect in time series things like seasonal patterns. So this kind of sinusoidal pattern happens very often in seasonal patterns, where you might see sales increasing and then decreasing. So this means that the residuals are not independent, and we need to find maybe some other model which can take this into account. Because essentially performing inference when we violate this assumption means that our results are garbage. We can't really trust the p-values. This slide summarizes the procedure we need to follow to develop a linear regression model. The first step is to develop a model that has a theoretical basis. We assume that we can predict a variable from some other variables, and obviously this needs to actually make sense in the real world. So let's assume that this is out of the way, and now you can move to the second step where you start to develop the model. You can do some scatter plots to see whether really the input and the output follow a linear relationship. Then you can run some scatter plots to identify potential outliers, which you might have to remove. Then you can assess the multicollinearity between the variables, whether it exists or not. After that, you determine the regression equation. And after you fit the equation, you run the residual tests in order to check the required conditions to see whether the regression assumptions hold. Obviously, you also need to check for the model's performance through the adjusted R-squared and the F-test for the overall regression model. And if these are significant, then you can go ahead and see the significance tests for the individual coefficients in order to understand which variables are important for predicting the response variable, the target variable, and what is the direction of the effect.